welcome to The Explainer. Today, we're going to take a journey right into the heart of matter itself to get our heads around the one concept that really underpins everything, the atom. It's probably one of the oldest, deepest questions humanity has ever asked. For thousands of years, all we could do was guess. But over the last couple of centuries, we started to find the real answer. And believe me, it is way stranger and frankly more beautiful than anyone could have ever imagined. So get this. Long before we had microscopes powerful enough to even dream of seeing an atom, scientists back in the 18th century were already finding clues. They were discovering these fundamental laws of chemistry that just didn't make any sense unless matter was made of tiny, indivisible little particles.
And what's so cool is how these two pretty simple-sounding laws basically forced science into a corner. First, Lavoisier proves that matter isn't created or destroyed in a chemical reaction. Then Proust comes along and shows that compounds always have the exact same proportions. The only way both of those things can be true is if matter is built from discrete little units, what we now call atoms.
Okay, so the atom was real. But for a while, everyone just pictured it as this solid, unbreakable little ball. The next huge leap forward was realizing that this unbreakable ball actually had parts. It was time to crack it open and see what was going on inside. And here they are, the cast of characters. It all started in 1897, when J.J. Thomson found the teeny tiny negatively charged electron. Then came Ernest Rutherford's legendary gold foil experiment, which revealed this dense, positively charged center, the nucleus. And eventually, inside that nucleus, we found the positive proton and then the neutral neutron, thanks to James Chadwick. All the pieces were finally on the table. And just to give you a feel for the scale we're talking about inside this tiny world, a single proton is about 1,837 times more massive than an electron. I mean, that's like comparing a bowling ball to a single grain of sand. This massive difference is absolutely key to how an atom is put together. All right, so we've got protons and neutrons packed into a heavy nucleus, and these lightweight electrons are buzzing around somewhere. The next giant question was, well, how does it all fit together? And that kicked off this big race to try and build a model that actually worked. So Rutherford, he made this really intuitive leap. He looked at the massive nucleus and thought, that's the sun. And the tiny electrons? They must be the planets orbiting around it. It's a simple, elegant picture, right? A really brilliant first guess. But it had one fatal flaw. See, according to the physics they knew at the time, a charged particle, like an electron, if it's orbiting, should be constantly losing energy. It should spiral inward and just crash into the nucleus in a fraction of a second. So if this model was right, atoms, and therefore you, me, and everything else, shouldn't even exist. Something was seriously wrong with the picture. And this brings us to Niels Bohr, who came up with a totally radical solution. He basically said, what if electrons can't just be anywhere? What if they're restricted to fixed energy levels, like steps on a ladder? They can jump from one step to another, but they can't exist in the space in between. And that one idea, that single change, suddenly made the atom stable and perfectly explained the weird light patterns that hydrogen gives off. Bohr's model threw open the doors to a whole new, kind of bizarre but incredibly powerful set of rules that run the subatomic world, quantum mechanics. And it turns out an electron's position isn't some neat little orbit, it's more like a probability cloud that's defined by a very specific set of codes. The best way to get a handle on this is to think of an electron's place in the atom as its unique address. Now, this isn't a single point in space, but more like a neighborhood. And this address has 4 distinct parts, which we call the 4 quantum numbers. So let's build one together. First up, you have the principal quantum number, which we call n. Let's think of this as the state or province in our electron's address. It tells you the main energy shell. The bigger the number, the further that electron generally is from the nucleus. Okay, next up we need the city. This is the azimuthal number, L. This number describes the actual shape of the orbital inside that energy level. Is it a simple sphere, or is it a more complicated dumbbell shape? So we've got a state and a city. Now we need the street name. That's the ML, magnetic number, and it tells us how that orbital is oriented in 3D space. Which way is that dumbbell shape pointing? North-south? East-west? And finally, the house number. That's the spin number, or m sub s. Each one of these orbitals can hold 2 electrons, but they have to have opposite spins. We call them spin up and spin down. This is the last little detail that makes every single electron's address totally unique.
And all of this leads to one simple, unbreakable law, the Pauli exclusion principle. What it means is, no two electrons in the same atom can have the exact same four-part address. Every single one has its own unique spot in the quantum world.
So how do atoms actually use these addresses to build themselves up? Well, nature is pretty efficient. It follows something called the Aufbau principle. It just means that electrons always fill the lowest energy spots first. It's like building a house from the ground up in a very precise and predictable order. Now that we've got the rules down, let's just take a second to appreciate the scale of all this. A typical atom is about 1/10,000,000th of a meter across. It's a number so small it's almost impossible to really picture. But the real shocker is when you look inside. The nucleus, way down in the center, is 10 to the minus 15 meters. That means the nucleus is 100,000 times smaller than the atom itself. To put it another way, if an atom were the size of a giant sports stadium, the nucleus would be a single marble sitting on the 50-yard line. The rest of it is just empty space, defined by the probability clouds of its electrons. So why does all this bizarre quantum theory actually matter? Because understanding these strange rules is exactly what unlocked our entire modern technological world. The way electrons behave inside atoms isn't just some abstract idea, it's literally the engine of our reality.
Hey, remember Bohr's energy levels, those steps on the ladder? Well, when an electron drops from a high step to a lower one, it has to release that extra energy. And it does so by spitting out a photon, a little particle of light. That single quantum leap is the basic principle behind every LED screen, every laser, even the colors you see in fireworks.
And it goes so much further than that. When you smash high-energy electrons into a target, they can produce powerful radiation, like X-rays. And because we understand that atomic process, we can do incredible things. We can see broken bones inside our own bodies, inspect airplane parts for tiny cracks you could never see, scan our luggage at the airport, and even read ancient, fragile scrolls without ever having to unroll them. And that's really the bottom line here. Every single computer chip, every MRI scan, every light bulb in your house, it's all built on our understanding of these deep, fundamental rules of the atom. It kind of makes you wonder, right? What other secrets are still locked away, just waiting for us to find them, inside the fundamental building blocks of our universe?